Everyone had a lovely lunch. Here we're about to hear from Huon, who has done work for some very big names, including Apple, Cyro, and so on. He's going to give us a talk about packaging for serverless. For serverless, because that must be easy, right? We've all done that. All right, if you're ready,
yeah,
take it away. A round of applause.
Thank you. You know that nightmare where you're standing in public, speaking in public, and you realize you're not wearing any clothes? At Exoflare, we were living in a bit of a nightmare. It was taking embarrassingly and frustratingly long to build our artifacts for our AWS Lambdas. But we woke up and we put our pants on. By adopting the pants build system, we made that process effortless. I'm Huon Wilson, and this is Sterling, our corgi. At the moment, I'm working for Exoflare, which is a software company trying to make biosecurity easy. So we're reducing the risk and severity of animal diseases. At least that's what we're trying to do. I'm mostly writing Python as a back-end engineer, but I'm also doing front-end, I'm doing data science, and I'm doing DevOps. As a bit of a disclaimer, I'm now a pants maintainer. So this talk will be about this pants build system tool. But when we were evaluating pants to work out what tools to use, I had no connection to it. As part of that adoption process, I filed enough bugs, contributed enough fixes, that I was nominated to become a maintainer as well. For Exoflare, I've worked on compilers and developer tools at Mozilla and Apple, and machine learning at CSIRO. Over the next half an hour, we'll remind ourselves what AWS Lambda and similar products are, and we'll work out why Python, an interpreted language, needs a build system. Then, we'll look at the conventional wisdom for doing that build system, which is using pip install, and we'll see why it's slow and fiddly. And then, I'll talk about the solution we really enjoy, which is using pants. Sound good? Let's get into it. Functions as a service is a bit of a silly name, but it seems to be the accepted category name for tools like AWS Lambda, Google Cloud Functions, whatever the other cloud providers offer in this space. At Exoflare, we mostly use AWS, so I'm going to say Lambda throughout the talk, but I think most of the lessons will apply to the different products. I just can't speak to them personally. So a Lambda is effectively a snippet of code. It could be a dozen lines, it could be a dozen megabytes that you upload to the cloud provider, and then they'll manage sort of invoking it for you and setting up the interpreters and all that stuff. We use it for things like cron jobs, so some cleanup that happens every hour. We use it for some event processing, and we use it for integrating with the cloud provider. So when we do our deploy with a cloud formation, we have some custom resources. And AWS makes it easy to back those custom resources with Lambdas. This talk is about serverless, but it's not saying microservices save the world, or that you should use serverless for everything. We use Docker images for other things. We only have a few Lambdas for different problems we solve. This talk is about, if you are using Lambda or other serverless offerings, maybe you can learn from the suffering we went through and the solution we found. Let's make this concrete. So here's an example of a Lambda. The details don't matter too much, but it takes in a bit of JSON, message, then some string, and then we'll return that string. So message hello, returns hello. I personally don't like parsing JSON myself. I don't want to check that the message key exists. I don't want to check that the value is a string. So we use one of these libraries, a bit like Pydantic that was referenced in earlier talks, that lets us define the structures more declaratively. The last piece of this is a handler function. So this is what AWS will invoke to actually get our Lambda to do its thing. The details of that don't matter too much, but what does matter is that this message spec library, so the thing I'm using for manipulating the JSON, that's an external library. It's from PyPI. When we have an external library, we need to specify our dependency somehow. So we could use pyproject.toml, we could use a pip file, but we'll keep it simple for these examples and just use requirements.txt. So this defines our Lambda. We've got requirements.txt with our message spec dependency, and we've got our actual source code. Sounds pretty good. And we could hypothetically get this into AWS somehow and invoke it, and it would give the right behavior, in theory. But you'll notice that the way to get it into AWS is either a Docker image, which has some downsides, or zip files. We use zip files, so that's what I'm going to talk about in this talk. The zip file has to have a particular format. So the format has to be, of course, our source code has to be in there somehow. So we've got echo.py in our echo.zip for our echo lambda. And we have to include all of the source code of the dependencies. So our echo lambda uses the message spec dependency, and thus we need to include its source code. This is why we need a build system for Python. So what we had in our repository, that was echo.py and requirements.txt, that's different to what goes in this zip file. So we need some sort of a system for building a zip file that has the right format. Suppose we have a system, then we get a zip file and we can upload that to AWS somehow. So we could use the console, we could use the command line interface, we could use Terraform, we could use CDK. There's all sorts of tools that will let us take code on our disk and put it into the cloud. But that's not the focus of this talk. The focus of this talk is turning our source code in our repository into a zip file ready to upload into the cloud provider. If we look through the AWS documentation, we can work out a system for doing this. So this is a script I've distilled down. First we go pip install our requirements into the package folder. Then we can copy in our own source code, so copy echo.py into that folder, and then at the end we zip it all up. And this gives us echo.zip. If we were to look into this zip file, just like with our normal computer investigation skills, we could notice that it has basically the format that we were just discussing. So it will have our echo.py in it, and it will have the source code of the message spec dependency in it too. Let's upload it to AWS, let's invoke it, and we get an error. No module named message spec._core. That's a bit weird, because when we look in the zip file, there is a file that looks pretty related. Message spec/_core. That sounds like it matches up. But a bit further in the file name, it says Darwin. Darwin's another name for the Mac OS operating system. Lambda is running the Linux operating system. So when I ran these commands, this pip install build script on my Mac machine, it chose code that is specific to Mac. And that won't work in Lambda. Understandably, the Lambda Python interpreter is ignoring this module, doesn't want to try and run Mac-specific code on the wrong operating system. Okay, well, we can fix this using Docker. Docker for Mac makes it easy to run Linux virtual machines, commands on Linux while on Mac. So we can go Docker run, some arguments to get our source code in, choose an image, one provided by AWS, seems pretty plausible. Use our script. If we run this, we get out another zip file. We get our echo.zip, version 2, I guess. When we upload this to AWS and we invoke this, we get the same error. But we know where to look now. Message spec/_core, blah, 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 Linux. So we've got the right operating system, but it says ARCH64. That's a reference to the ARM CPU architecture. Lambdas, at least by default, will run x86 64 or Intel CPU. So we've fixed our operating system mismatch, but we still have a CPU mismatch. The fix is easy enough. We add yet another argument to our Docker command. We run the build, we upload to AWS, we invoke it, and we're victorious. We finally have a working Lambda. So we invoke it with message hello, we get back hello. Very cool. We now have somewhat of a build system. We could probably make it a bit more general if we wanted to actually be a system. But we've got something that can produce functional zip files that work in Lambda. Unfortunately, functional is just the minimum bar for a build system. Performance is important too. No one wants a slow build, right? This is the performance of the 3 different steps we ran. So we see that running natively on my Mac, the very first thing we did, that took about half a second. But it gave us a zip file that didn't work, so it's just taunting us. Running on the ARM Docker took 3 times longer. But again, it's taunting us because the zip file doesn't work. To actually get a working zip that gave us a working Lambda, it takes us 5 seconds. This is because it's having to run a virtual machine that's emulating the CPU. This comes with significant overhead. 5 seconds would be tolerable if it was only 5 seconds, but it gets worse. Imagine we're adding a second Lambda. So a feature request has come in that we need to do some reporting. That reporting is generating a plot. So let's add, we start with our echo.py and we've got our requirements.txt. Let's add a new file, plot.py. We're generating a plot, so we'll import matplotlib, another library from PyPI that is helpful for generating plots. It's in the name. It's from PyPI, so we better add it as a requirement. So this is now our pair of lambdas. We've got echo.py for our echo lambda, we've got plot.py for our plot lambda, and we've got the requirements required for both of them. We can tweak our build system to also be able to build the plot lambda and look at its performance. It's got far worse. Running natively on Mac, so that's as fast as we can go. Takes about 7.5 seconds. But to get a zip file that works, because this plot lambda has exactly the same platform-dependent code issue, to get a zip file that works, it takes 100 seconds. That's a very long time, and no one wants to wait for a build that long. Why is this one so much slower? So our echo lambda used to build in 5 seconds, this one builds in 100 seconds. Well, the plot lambda is using matplotlib. Matplotlib refers to other large libraries like NumPy. What this means is that the final zip package is almost 50 megabytes. For the echo lambda that we had before, it was like 200 kilobytes. That is a huge amount larger. Manipulating all that extra data is going to take extra time, and we can see it on this graph. This graph is nominally about the plot lambda, but it's actually, by adding the new dependency to our requirements file, we've made the echo lambda really slow too. When we build the echo lambda, we installed the requirements from this file. So we install message spec, that's what the echo lambda needs, but we also install matplotlib, even though the echo lambda doesn't need matplotlib. So we spend 100 seconds manipulating and installing matplotlib for no reason. Not only that, but the echo lambda zip file went from 200 kilobytes to almost 50 megabytes. A larger zip means slower uploads to AWS, and it also means slower cold starts. So when a lambda starts for the first time, it has to initialize the system, and that takes longer when you have a larger deployment package. So preferably, we would prefer not to be spending 100 seconds building echo pointlessly, and we would probably also prefer not to be spending 100 seconds building the plot lambda. We can solve one of those problems by splitting our requirements. So on the left, we've got our echo lambda, and we could have our echo.py file plus the requirements that that file needs specifically. And on the right, we have our plot lambda and the requirements plot needs specifically. If we do this, now the echo lambda will be back to building in 5 seconds. The plot lambda will still take 100 seconds to build, but at least with half the time that the total build process will take. This can work, but it gets harder as soon as we start trying to share code. So imagine we wanted to do logging in the same way from both lambdas. So we have some logs.py utilities, and in particular, we want to do structured logging. So logs.py imports structlog. Structlog is yet another library from PyPI, so we better make sure it's installed in the lambdas. If it's not included in the lambda zip file, then echo.py will import logs.py. Logs.py tries to import structlog. Structlog isn't available, and the lambda crashes. One way to do this would be to remember which lambdas we need to, which lambdas are using logs.py, and go and add it to all of those requirements. But whenever we say remember and expect humans to do it, that's always a losing proposition. It's easy for us to forget to do something. Like if we hadn't added it to the echo requirements, then echo would crash. This is fiddly, this is annoying, and it's still not solving the problem with the virtual machines. There's other ways to solve this problem too, like you could have sort of a shared set of requirements. So you have your logs.py with its own requirements, and then when you build the echo lambda, you install the shared requirements and the requirements specific to echo. And that's basically what we were doing at Exoflare. But even that is fiddly and definitely doesn't spark joy. So we've looked through the conventional wisdom, and we've looked at it in detail. There's tools like AWS CDK offer sort of packaging for Python, where it can wrap up this process. But under the hood, it's basically doing the same thing. Last time I checked, it was still using Docker to run pip install. The impact of this is our cross-platform builds are really slow. And when we have multiple lambdas with different dependencies, we can either end up with unnecessarily slow builds and unnecessarily huge zips if we include dependencies that Lambda doesn't need, or we end up with a world of really fiddly dependency management and having to remember to update 10 different files whenever we make a change. At Exoflow, we were trying to optimize our build times with that fiddly approach, but we still took us 3 minutes to build our infrastructure before deploying, and worse, when we were trying to test it locally, it will take 5 minutes to test our infrastructure. That is not very pleasant. So we looked around for solutions, and we settled on the Pants tool. Bills itself as the ergonomic build system, and that seems to be true. So we use it for things like running tests, running code linting, running code formatting, but most importantly, building artifacts. So Pants is the build tool we use for turning our source code into zip files, ready to upload to AWS. As we were adopting Pants and evaluating different tools, we of course asked questions like, what tools are available, how do we use these tools, and how do we adopt them incrementally to start seeing benefits earlier. But we then asked, how would Sterling wear pants? My wife thinks number 3, I reckon number 7, but I'm told that those are overalls, not pants. But more seriously, we asked, what performance improvement would we see? So this is the examples we had, the example lambdas we had before. It would take 5 seconds to build the Echo Lambda using Docker. With Pants, it takes 2 seconds. That's a nice speed up. But more significantly, the plot Lambda would take 100 seconds to build with Docker. It now takes less than 8. That's a huge speed up. Most of that 100 seconds is spent manipulating dependencies, manipulating matplotlib, manipulating NumPy. Pants is able to do this natively without having to run in a virtual machine and without having to emulate the CPU. So we're able to run natively on Mac and see that really fast performance instead of having to run virtual machines. As I said, this was mostly manipulating dependencies. So let's look at that in a bit more detail. Here's the PyPI page for message spec. On the left, there's a download files tab. When you click on that, you see a long list of files. It starts with source distribution, and then there's a long list of wheels, .whl files. When you run pip install, these are the files that pip can choose from. So when I ran pip install on my Mac, it would actually choose this wheel, where it says something about macOS ARM64. This wheel includes the platform-specific code that was causing problems at the very start. So this is where we're getting that Darwin file from. The fix, and what we need to be doing, is actually choosing this wheel at the top. So Lambda is running on Linux and it's running the x86 64 CPU. So we need to choose the appropriate wheel, the one that has the platform-specific code for that platform. As far as I know, the only way to convince pip to choose a particular wheel is to be running on the matching platform. That's why we had to have a virtual machine so that we could pretend to be Linux. That's why we had to have the x86 64 CPU emulation so that we could pretend to be matching that CPU. The magic of Pants via the related PEX project is that it understands the difference between the computer we're currently running on and the target environment. So we're targeting Lambda, that's Linux, that's x86 64. We can choose the appropriate zip and mash that up into the appropriate format, even if we're not running on that platform. So we can still run on Mac, but we choose this zip and then turn it into the appropriate zip file for AWS. This is why Pants is able to run those builds so much faster, because there's none of that overhead of virtual machines or CPU emulation. Sounds good? How do we adopt Pants? Let's go back to the simplest version of the 2 lambdas that we had, where we had our echo.py and we had our plot.py with our source code. and then a single requirements file that contains all of the requirements required. To start using it, we first add a pants.toml, which specifies some global configuration, like which pants version we're using. And we also add a build file. The build file basically tells pants, like, here's my source code, here's what you should be paying attention to. So we need to say two things. We say Python requirements, which will pick up our requirements.txt file, and we say Python sources, which will pick up the two .py files. Once we've done this, we've now told pants about our Python code. And in theory, if we had any tests, we could run those tests. But we don't care about tests. What we care about is building Lambdas. To do that, we activate the built-in Lambda backend, and then we define the two Lambdas we want built. So the configuration is a little bit overwhelming here, but it's simple enough. We say it's Python AWS Lambda function. We need to configure two things. We need to give it a name, so echo for the echo Lambda. And we also need to tell pants where to find the handler function. So the handler function is in echo.py, and it's called handler. We need to do the same configuration for plot. So we say, call it plot, find the handler function in plot.py, please. This is enough to define our Lambdas. So we haven't had to write any shell scripts. We haven't had to fiddle around with Docker. And this is indeed the dozen lines of configuration that I was using to run those performance benchmarks we saw before. Were driven off this configuration. To actually do the build, we run one command, pants package : : When we do this, it takes about 8 seconds. There's some streaming output. I've trimmed it down to what's interesting. Let's walk through it step by step. First, we can see we meet the minimum bar for a build system. It's functional. It's produced our two zip files. So we've got echo.zip, we've got plot.zip. We can upload those to AWS, and we've got working Lambdas. There's something that was missing from the configuration on the previous slide. We didn't have to say anything about message spec. We didn't have to say that echo uses message spec. We didn't have to say that the plot Lambda uses matplotlib. What pants has done is it's inferred the dependencies. So it actually looks at our echo.py file and observes that there's an import message spec line in there. It understands this is a reference to our requirements. So it knows that that's to run the echo.py file, you'll need to have message spec available. And thus, when we build the echo Lambda, pants makes sure to include the message spec library in that Lambda. There's no other import statements in that file. There's no import matplotlib, so matplotlib doesn't need to be included. Thus, dependency inference means that our Lambda is automatically including only the dependencies that it actually needs. We're solving that problem of accidentally having larger builds than necessary. The same process applies for the plot Lambda. So pants has looked into the plot.py file and observed that matplotlib is imported. Therefore, it better be included in the Lambda. Let's talk about performance, because performance is the next bar above functional for a build system. The total build took about 8 seconds, and 8 seconds is less than it would take to first build echo, which was 2 seconds, and then build plot, which was also about 8 seconds. What's going on here? Well, instead of building them one by one, it's not going echo, then plot. Pants is automatically building these in parallel, so it's building echo and pants at the same time, echo and plot at the same time. Parallel is nice. It doesn't make too much of a difference for these Lambdas, but if you had more, it would make a much bigger difference. When we're talking about performance, we better run things multiple times. So if we run pants package again, it gets so much faster. What's going on there? Well, pants has built-in caching. The first time we ran the package command, we had to run builds. So we started with echo.py and plot.py, and we built our zip files. That would take 2 seconds and 8 seconds. They ran in parallel. When we ran it the second time, we haven't changed code. We haven't changed configuration. So instead of having to build the things again, pants understands the inputs are the same, therefore the outputs will be the same. This happens so much quicker. It's just copying files around rather than having to build, actually do the expensive build process. This happens in a fine-grained way. So if we had changed echo.py, imagine we'd added a feature to our echo Lambda, but we've left plot as it was. When we ran this, when we were to package this again, the plot Lambda would still be cached because we haven't changed any code that affects the plot Lambda. The echo Lambda has changed, so we need to run that build, But now the whole process takes 2 seconds and still gives us all of the zip files that we requested. This caching applies to more than just building packages. So we use it for testing, we use it for linting, and the caching applies to that as well. Caching is the first of Pants's performance powers. So caching means that Pants never redoes work that it's already done. When Pants is running a process, it's usually because it has to. It's new work. The next performance power is parallelism. So when work has to happen, it happens in parallel. The third one, surprisingly enough, is dependency inference. Dependency inference is what ensured that we did the minimum amount of work possible. Our Echo Lambda only included the dependency it needed to include. The final one, which is the one we saw first, is native execution. We're not having to do virtual machines. We're not having to emulate CPUs. So the work that needs to run is run. It runs in parallel. It's the smallest amount of work possible, and it runs as fast as possible. That makes for a happy developer. For our system, this is the impact it had. So remember how I said our builds were taking about 3 minutes before? Now they take about 90 seconds. And this is actually happening already on Linux. So this is all because of parallelism, and it's all because of the dependency inference reducing how much work happens. Far more significantly, though, when we're testing our infrastructure locally, previously it would take us 5.5 minutes. And that's mostly because we would be building and rebuilding Lambdas pointlessly every time we ran tests. Now, Pants's caching kicks in. So instead of having to rebuild a Lambda that's already been built, it just gets served out of the cache. Thus, our tests take 10 seconds instead. That's much more enjoyable. In summary, this is about as much clothing as we could get on Sterling. He's not going to wear pants. He barely tolerates his harness. But actually, at Exoflare, we saw that when we adopted Pants, using it for building Lambdas, it dramatically reduced our build times and our test times for our infrastructure, as well as keeping our configuration really simple. Exoflare has a strong open source mindset and understands how important it is, such as me contributing to Pants, as well as paying for our dependencies. And please come and talk to me if you're interested in biosecurity, if you're looking for a job, and just generally if you want to have a chat. The code examples and some more links are available in this repository. Thank you very much.
Unfortunately, we haven't got enough time for questions, but I'm sure you can find Huon out and about in the conference if you have any further questions on the topic.
Yeah, please chase me if you have questions.
As a thank you, we get a speaker's gift of a cup.
Thank you.
Thank you, guys. Thank you very much.